the observed flux drops like the distance, like 1 over distance squared. And this is simply, here, if I'm nearby, the car looks very bright to me, but the car far away has the same luminosity, namely the light bulbs are the same, but the photons have to cover bigger and bigger sphere, and so the observed flux is smaller. So again, if I have some object, a standard candle, which has known luminosity, this is known, this is observable, I can invert this equation and then measure the distance. Nature provides, as it turns out, there is several kinds of standard candles in astronomy. They're not as perfect as 100-watt light bulbs, namely they have certain dispersion. They're not all exactly the same luminosity, but they're pretty good. One very commonly used standard candle is called the Cepheid, and namely it's named after a star in constellation of Cepheus, and that star is variable and changes certain way. And Henrietta Swan-Leavitt almost exactly 100 years ago has discovered that the Cepheid variables obey what we call period luminosity relation. This is kind of, doesn't really matter in the detail, but we can use the fact that how quickly a Cepheid varies is related to its luminosity. If I observe Cepheids near the sun, and I measure their distances from the parallaxes, and now I observe the same Cepheids in faraway galaxy, I can measure their flux, I know their luminosity, I'll be able to measure distances. So this method, almost immediately, she discovered the relation in 1912. Her boss at the time, oh no, actually he wasn't yet. He would become her boss down the line. But there was astronomer Harlow Shapley. He used that idea to measure distances to objects in the Milky Way. Before he started measuring distances to what we call globular clusters, which are this very dense concentration of stars in the Milky Way, but they're not in the plane of the Milky Way, people thought that our Milky Way is maybe a few thousand light years across. It's big, but not by current standards, it wouldn't be very big. He started using the Cepheid method or the standard candle method to measure distances to globular clusters, and what he found out two important things. One is that Milky Way is 100,000 light years across, or 30,000 parsecs. The second important thing, and that's still true, is that we are not in its center. We are about, by his measurement, we are about 1/3 of the way towards one of the edge of the Milky Way. So at the time, really, this was a profound discovery because, yet again, just like Copernicus has sort of removed the Earth from the center of the solar system, Shapley, by measuring distances to globular clusters, he says, Sun also, there is no reason Sun should be in the center of the Milky Way. In fact, it's kind of in some random place in the Milky Way. It's 1/3 of the way towards the edge. And so this was a very important discovery. So at this point, we have a pretty good idea about the size of the Earth, size of the solar system. We have measured distances to nearby stars through parallaxes, and we use that to calibrate what we call the standard candle method to also measure distance of the Milky Way. But at the same time, Shapley says, well, the Milky Way is so big, that's probably the whole universe. There's nothing outside, so everything we see on the sky is part of the Milky Way. It's a really big object, again, 100,000 light years across, maybe more, but that's it. There's nothing outside it. At the same time, other astronomers were debating this idea. There was, in fact, I'll skip this. There was quite a famous debate, I believe, in 1920. So Shapley was saying Milky Way is the universe. And another astronomer, Curtis, was saying, well, there are these things we call nebulae. For example, Andromeda Nebula. It's now called, it's an object called M31. There are other nebulae. They look kind of like spiral, objects. We don't know what they are, but they said they are just like Milky Way. If we looked at Milky Way from outside, it would appear to us like one of these spiral galaxies. And they had a debate. They met. They talked. Shapley won. Namely, he was a better debater. Turns out that Curtis was right. This again tells you that science, it's good. It's a good thing to be a good speaker. But really, down the line, what's important where you write, namely, did the data support what you said? How did that happen? And this is where Edwin Hubble made one of his many contributions. He, again, it's good to be smart, but also you need to have a tool. He was, at the time, he was briefly here working, I think, in New Albany as a teacher. This is across the river. But he then went back to Chicago to get his PhD, and then he ends up working in California. At the time, they just commissioned the biggest telescope on Earth, which is 2.5 meters, so 100 inches diameter. And with this telescope, now you could see Cepheid variables in nearby galaxies. So he famously, by the way, I think there are several houses. He only lived here for 3 houses in Lexington. He only lived here now and then. One is nearby the campus.
Two are right here in Louisville, and one's in Shelbyville.
Okay. And he is. I think he was also taught. He was a basketball coach for that year that he worked but he was teaching science as well. And this is New Albany. What he does now, this was 1914. This is now 1923. He takes images using photographic plates and the new 100-inch telescope of Andromeda Nebula, and he takes many such images, and he discovers that some of these stars are actually variable. They don't stay put. There are these what we call Cepheid variables. By measuring how bright, or rather how faint they are, he can derive a distance to Andromeda Nebula. And that distance, although very incorrect by today's standards, this is about factor of 3 too short, is still much, much bigger. This is almost 1 million light years than the galaxy that Shapley has measured. So by measuring the distance to M31, which is much bigger than any possible size of the Milky Way, Hubble immediately shows that the universe is much, much bigger than Milky Way, because this is the nearest galaxy to ours. This is the biggest galaxy in the sky. There are thousands and millions of galaxies, or Carl Sagan used to say billions and billions of galaxies in the sky. I'm too young for that, but apparently that was in the 80s. And some of these galaxies are tiny. And so if the biggest galaxy on the sky, and they were probably the closest, is already much farther away than the size of the Milky Way, then the universe really has to be vast. And it's full of galaxies. It has millions of galaxies just like the Milky Way. This is huge. This is, again, Shapley was huge. The Milky Way became much bigger, and also we're not center of it. Suddenly, overnight, again, always takes a few years in science for people to accept it. Other people have to do it, and so on and so on. But this result, of course, has held up. Now, universe suddenly is really millions, and if not billions, of light years across, just because there are objects in it that are so far away. And so here's a little animation we did with graduate students some years ago of another galaxy Hubble also observes called M33. It's in triangle. And as you can see, this is, of course, speed up. Usually the Cepheid takes several weeks for it to change its brightness. And here most of the stars don't vary, and now and then you can see some variable stars. That's basically the measurement you do. You take a whole bunch of plates. At the time, now we use a CCD frame, just like the detectors you have in your digital camera. We take images, and most of the objects don't vary, but some of them vary. And we can measure the period of variation, and then we can use the period luminosity relation to measure the distance. So now, let's say 1926, he published a series of papers. There was another 1929. He shows again and again, and other people as well, that the universe, the distances to nearby galaxies are vast. They're much farther away than they couldn't possibly be in the Milky Way. The other thing that's happening is that there is a general theory of relativity. That's 1916 by Einstein. For the first time, we have a way to describe the fate of the whole universe in a very simple way, actually. We can write equations, and we can treat the whole universe as one object, and we can write equations for the distance between any two objects in the universe. And there are only 3 possible solutions. One is any 2 points in the universe can be coming closer together. They could also be moving apart. And then, if you allow for the special term, and Einstein introduced especially for that, called lambda, you can make the universe static, which at the time he thought the universe was static. So he introduced this term called lambda to make the universe static. Because, of course, people actually thought the universe didn't expand or contract. So therefore, his equations, which were to describe the universe, needed this extra term, which he called lambda. Other people didn't like lambda, and they said if you don't have lambda, then the universe should be expanding or contracting. So in some ways, there were already predictions even before people went and measured either expansion or contraction that the universe should be evolving. The universe either is contracting or expanding. Einstein didn't like the idea, hence he introduced this term lambda. So here is Edwin Hubble again. he already has a program. Of course, this happens at the same time. We never really we do things, we sometimes work on several projects at the same time. He has a program to measure distances to nearby galaxies. He uses this distance to measure distance to even farther away galaxies where he couldn't measure Cepheids, but he would use what we call secondary or tertiary methods to measure their distances. At the same time, he is performing much simpler experiment, namely he measures how quickly these galaxies are moving either towards us or moving away from us. And that's because we have the thing called Doppler effect, namely if something is moving towards me, the light will be blue shifted, and when something is moving away from me, the light becomes red shifted. This is not his discovery. This, of course, is a well-established method. But again, he has the biggest telescope of any astronomers. And so he systematically takes spectra of galaxies. At the same time, he measures distances to them. And now in 1929, for the first time in history, somebody says there's actually there were other papers, but he had the best data to really say it, and people believe him, that there's a relation between distance to a galaxy and its recession velocity. And there are some galaxies which are actually moving towards us, so they are below zero here. Zero means it's standing still. Negative means it's coming towards us. But most of the galaxies are moving farther away, and the farther away you are, the faster away you're moving from us. The entire universe is expanding. So